Oh, thanks for this nice introduction and also for the invitation. Usually I give talks to wireless people. Now, I have to give a talk to people working in robotics. It was a little bit a challenge, but I hope you enjoy. So the title is Consensus-Based Control of Multi-Robotic Systems over Wireless Networks. My name is Slawomir Stanczak, and first of all, I would like to acknowledge the main contributors and collaborators. You can see them here, especially Navnet Agrawal, but also Renate Cavalcante, and also past collaborators. Those people are not here with me anymore, but still active. And I remember Professor Reich is he professor at TU Berlin in control theory. So, okay. And the first disclaimer is that the talk deals with the challenges of wireless communications and edge inference in large-scale collaborative robotics, not robotics itself. So it's not it's not a talk about robotics, but I still think that it's quite interesting and very relevant to this area, especially collaborative robotics. And also, there are some related topics like physical AI, edge inference or edge AI, split AI, whatever. And okay, my background is in control theory. I did study control theory with minor in robotics, but this was 3 decades ago. So since 1998, I have been active in wireless communications and signal processing. So, but still, I have some basic knowledge of control theory and robotics. Good. I mean, the storyline is like this. First, I would like to motivate that wireless communication can be, first of all, bottleneck in large-scale robotics if we don't do things properly. And then I will show, with one slide, limitations of current systems like Wi-Fi and then that they don't scale to dense real-time coordination, which is necessary in large-scale robotics. And then, okay, so there will be some observations, and basically, I think that in your area, it's well known that coordination can be formulated as a consensus problem. It's not so obvious in the area of wireless communications, but basically, this is what I would like to motivate with some slides. But at least control engineering guys, they know that that coordination is a consensus problem. So you have this consensus control works, but in my opinion, the people too strongly abstract physics. I mean, in particular, the wireless communication channel. So that's why the performance is, I would say, the performance doesn't scale properly to if you, for example, increase the number of agents or robots in your system, and that's I will try to show how to what would be the the approach to cope with this bottleneck. And the insight is, of course, only task-relevant information is needed, and which is, much smaller than, raw data. And then this would lead me to task-oriented communication with over-the-air computation, so which is the basis for scalable and efficient coordination in the context of large-scale robotics. And then I will show some demos we have and what we do, but I will start with some, let us call this theory, right? Okay, so maybe the first slide, I don't know whether it's necessary to show this, but from our perspective, we see rapidly growing demand for collaborative robotics across domains such as home automation, autonomous driving, and industrial logistics. and the market is expected to increase significantly over the next decade. I mean, this is what we assume, and this creates a fundamental challenge for wireless systems. Especially, I am talking about mobile robots where you cannot use cable; you have to communicate over the air in principle, right? So here, what I have to, you probably don't see this, but yeah, so such multi-robot systems require tight coordination, and then here there is this video we found at LinkedIn, which is quite funny. And the coordination relies on wireless communication. This is what I said in mobile robotics. Now, because you don't want to have cables, you want to be flexible, and so on. And but communication can be a bottleneck. I mean, which is shown in this video. I mean, particularly what you would like to have is some kind of low latency, reliable communication with guarantees, right? I think that this is important, especially if you deal with some kind of systems you have to keep stable over time and so on. So communication can be bottleneck. And of course, I mean, if we talked about robots, also for me, drones are robots, and here there are some other applications. In particular, formation control is the problem of coordinating multiple agents to maintain a desired geometric configuration while moving, and each agent uses local information from its neighbors to adjust its motion without relying on centralized control. I mean, this would be distributed formation control. Here, I would like to emphasize that in many cases, it's important for, especially for time-critical systems, they require spatio-temporal robustness. So it's not about only to avoid collisions, to have this spatial coordination, but also it's important to satisfy some strict deadlines, and so it's about latency. Another example is surveillance and environment modeling. Here you can see, you have drones monitoring an area. Each drone has some kind of partial view, and then you can use the information from different drones to reconstruct the area or do some other things. Okay, but later I would say something about formation control, and but I'm not going to talk about this second here use case, surveillance and environment modeling. Good, and on the wireless side, probably I mean everybody, each from you has a smartphone, and but yeah, in the end, I mean now I would say that wireless communication is a key technology for future digital infrastructures. It's not about smartphones or connected people. It's also about connected people and machines. So you have something like called Internet of Things. I think that it will play some role in the context of autonomous vehicles. We have Industry 4.0 with private 5G networks, logistics, e-health, and so on and so on. So what we observe is a rapid growth of mobile data traffic. So you can see here on the right-hand side from one report, and now we also expect further boost with due to on-device AI. Now I think that Apple announced something 2-3 days ago, and this is okay. I mean, great vision maybe, but from the technical point of view, it's not so easy because the traffic from devices to the base station is fundamentally different from the communication from a base station to devices. Yeah, because your smartphone, for example, it doesn't have such capabilities as a base station deployed somewhere on a roof of a building. Okay, so and what is the problem? The problem is that spectrum is scarce and very expensive. Now, frequency spectrum, it's limited. It's a limited resource. And if the traffic increases, then you have to use the spectrum more efficiently. Otherwise there will be some upper bound. I mean, there's a Shannon theorem stating that there is something called capacity, and that you can transmit. There is upper bound on the amount of bits you can transmit per second and per hertz. So it means the spectrum is limited, and then if the traffic increases and then you don't have more spectrum, you have to increase, or you don't have to. One possibility is to increase spectral efficiency. So you use the resource more efficiently. You can also deploy base stations. You can have something like dense networks, but it's quite expensive. So many, at the moment, it's not an option. And because deploying base stations to have sites somewhere in the city, it's quite expensive, and people don't want to have base stations, on roofs of buildings and so on. So it's a big problem. Energy is another issue, of course. I mean, especially if you have battery-driven devices, so this is another resource which is limited. You have to be here. You have to, have some kind of resource-efficient way of operating to save, or to reduce the energy consumption. Another challenge is its mobility. Of course, this is relevant to mobile robots or scenarios with mobile robots, because if the device or robot moves, and then the environment changes very fast, sometimes on time scale of milliseconds. So you have to be very, very fast. And then on top of this, you have interference and something we called fading, which means that the channel is some kind of random process. I mean, it's medium that is not particularly nice, for transmission. It's a stochastic process that changes permanently very fast, and it's not only that it changes the distribution of this of the underlying stochastic process is not stationary, so it also changes very fast. In mobile scenarios, it can be like 10 milliseconds, 40 milliseconds. You have different distribution. And on top of this, okay, you have this high demands. I mean, you have applications with high demands, reliability, latency, and data rate. So I think that for mobile robotics or large-scale robotic applications, maybe data rates are not so relevant, but latency and reliability are highly relevant. And this is something we have to cope with. So now we have collaborations with people who work in this in robotics, and usually they say, okay, I mean, why is it a problem? Wi-Fi works well, or even Bluetooth sometimes they are used, for communication. Yeah, so it's okay, but Wi-Fi is insufficient at scale. And here we are talking about large-scale scenarios. Wi-Fi works in small controlled setups. I mean, you have one robot, I don't know, in a lab. There's no interference from other users or things like this. So then I think Wi-Fi is okay. But there are limitations in large-scale, dense, and mobile scenarios with real-time requirements. First of all, Wi-Fi, this is unlicensed spectrum, so interference and unpredictability. You don't have full control about this. Now, who is transmitting and so on? So there are some, say, methods to coordinate this access to the spectrum, but they are sometimes too slow. You cannot guarantee robustness that is acceptable for many applications. Then the access to the channel is, we call this contention based. So you listen before you talk. So first of all, you listen whether nobody is transmitting. and then you access the channel. But if you have, especially, of course, I mean, this requires this say implies some delay, but on top of this, you have some other problems like hidden node problem, and then you have collisions in the channel. So and then you have to repeat or start this process again, and this leads to huge delays. So it's not acceptable. It's a big problem. And then you have limited mobility support. You can do it, but it's not deterministic handover. It's like handover from one access point to another access point. It's not sufficient for many applications. So, and we are, especially, I think it's not sufficient for scenarios like this. So we call this distributed intelligence for large-scale collaborative robotics. And large scale means many robot groups operating simultaneously. So example, you have, 2-5 robots per group cooperating for a common goal. So like carrying objects and things like this. And then you have 100 or more groups, for example, in a factory. And then they just, they may cause interference to each other, but they are, fully mobile. And so you have to provide connectivity. Of course, I mean, I am not saying that the full intelligence is on the infrastructure side. Of course, I mean, robots are also equipped, with some intelligence inference. And then, of course, I mean, the question is, how to split, what is the functional split, how to split the intelligence between a device and the infrastructure. I will say something about this later. But this is basically, this is basically the scenario or a scenario example of a scenario we are interested in. And then we are sure, I mean, you cannot use Wi-Fi for this or Bluetooth, let alone Bluetooth, to provide, the desired connectivity. Okay, so then the question is, of course, can 6G support large-scale robotics applications? 6G is the sixth generation of mobile networks. This is something we are working on right now. Now, I mean, the current generation is the fifth generation. And 6G is more than communication, first of all. It's more than about communication. It's some kind of platform that should, where just, you have this strong convergence of communication, computation, and sensing. And then it matched this, say, physical world, digital world, and biological world, which is, basically humans. And so 6G, I try to say, summarize this in one sentence: real-time loop between world, which is, the physical world, data is virtual, like digital twins and humans. This is what 6G is about. So here there is a really simple illustrative example. First of all, 6G, of course, will provide performance gains in terms of latency and data rates, but this alone will not be sufficient. I think for the future applications of 6G, such as scenarios involving swarms of collaborative robots. And here, I mean, this is a simple example to illustrate that. Here the task is the robots. They don't compete. They collaborate for a common goal, which is about lifting, this object lying on the floor and carrying it to another location. So, and here the object, for example, should be carried as horizontally as possible. So this is a definitely consensus problem because they need to agree on position and speed. This is not competition, but this is a cooperation, right? And then we are working on. 6G should support such applications. And okay, so I was talking about challenges, but now, I mean, given this simple example, this toy example with these two robots, there are some opportunities, okay? And from my perspective, as a communication guy, first of all, coordination requires distributed data processing. So it's about computation. So you have distributed data at different robots, and the task is to compute a function of this data. And this, of course, can be formulated as a consensus problem. And and then, as I said at the beginning, I mean, it's widely known in control theory, but this traditional consensus is often too slow, and then existing acceleration methods are limited, so they are not satisfactory. I mean, they don't satisfy many requirements. So our approach is exploit interference. So interference, it's something bad, right? Interference. But it means that if you have two people talking at the same time, they interfere each other, right? So this is, or you have two transmitters, they transmit at the same time, they interfere with each other. But this is, interference per definition is can occur only if you have two devices or two humans, or I don't know, they are independent of each other. So they generate independent data, and then they will transmit the data or convey the data to another place where the data is fully reconstructed, right? Then this is interference. But if you have cooperation between robots, there is no interference, in fact, but still I call this interference, right? Because they don't compete, they cooperate. So, and this is, this is one opportunity to improve something in this context. So here, coordination control in multi-agent system, probably I mean, and then here consensus, they just fly in swarms, and then they need to agree on speed, altitude, and heading under local constraints. We have another example where leader follower consensus agents should follow a leader. So as I said, they here I mean, in such cases, there is no competition, there is only collaboration. But key questions are, which agent should perform which task based on which information, and how to efficiently exchange information between agents. And of course, I mean, maybe some of you is asking, now, okay, what the guy is talking about, I mean, there is no problem, right? I mean, you can transmit the data to a central point, and, communication, you say, okay, there is no problem. But when it comes to large-scale deployments with many robots, spectrum is extremely expensive and scarce. So that's why you have to take into account you have to answer these questions. You have to be careful what you do, otherwise you won't be able to satisfy the necessary requirements. So there's a toy example. Probably many of you know this. I mean, agents with single integrator dynamics, which means first order ordinary differential equations. I took, from this PhD thesis of Darina Goldin. I was a reviewer for this thesis 2013. And then, okay, so I took, the example of single integrator dynamics, but there are extensions to double integrator dynamics, which are, this is more relevant for many applications, but, here it's only about illustration, what the challenge or what the opportunities are. So here we have a control input of each agent directly sets the state rate. Now, so you can see here in this equation, UI is the control input, and then XI is just the state. And then you can dynamics are information driven, not physical, no inertia or physics is abstracted away here more or less. And application could be high level robot coordination, velocity controlled motion planners, and things like this. So, and then control input is based on neighboring states. So here I assume that, I have nodes, n nodes. They are distributed, and then they have states x1 to xn. And then in general, this control input is a function of this states. Not I wrote neighbor states, but in general, it can be a function of all states, right? In the network. So the question is, the function, this is the function to be computed over a network. Yeah. So, and then, what people usually do, they come up with a graph and edges. Edges, are communication links, and then for them everything is fine, right? So there is okay. I mean, what is consensus? There is a definition of asymptotic consensus. If all the states, they converge in the sense of this norm-induced metric, and then in particular here in the talk, I am interested in average consensus. So that you have asymptotically consensus, but on top of this, the states they converge to the average value of the initial states. Okay, and that these initial states are geographically distributed at different devices. So now, and this is the main point, the consensus protocol proposed, no, it's not proposed in this PhD thesis, but it's mentioned there, it has this form. So you can see basically the main observation, but trivial observation, you would say, is that the control input is, say, is a function of this local states, right? So you are not interested, in the individual states, but you have some function here. It's a linear function of these differences, but that's it, right? So that's, if you look at this, you can think, okay, I mean, I don't need to transmit all this, all the states to one place to compute, the control input. What I need to do is I need to know, this function, which is less information. So I will explain this, I think on the next slide. So, and in this thesis, for example, there is, I think it's not shown in the thesis, but it is mentioned in the thesis that average consensus is achieved if the graph topology and weights are chosen such that the network is strongly connected. So it's a basically directed graph, strongly connected, a weight balanced. So it means that these weights here, A, I, J, are symmetric. Right, and then you have this asymptotic consensus, and then even the average consensus. So what's the problem, right? The problem is, okay, one approach is gossiping algorithm, right? This is, I think, the simplest implementation of this, that you have neighbors more or less, and they exchange the data. So you assume that they have some states, and then they exchange, the states, and then they compute, the sum. And then if you think about the graph now with the edges, directed edges, and then the graph is strongly connected, then you can imagine that if you continue this process, it will converge to this consensus, and in particular to this average consensus. Okay. Another idea is broadcast gossiping. Here you have one guy that broadcasts the information to neighbors. So, and then they take this information and add to what they have locally. And then again, if you have, you have to model this properly using, graph theory. But if you have something related to this, strong connectivity, you will end up with asymptotic consensus and then even the average consensus in this case. So now if we take, like 16 sensors, or could be also robots, and see what is the convergence, you will get something like this. I mean, this is only, illustrative. Now, I don't know the parameters anymore here, but it's like, for comparison. So, but you can see that the convergence speed is not, good enough. I mean, one observation is that you have this, it's in German, randomized gossiping, and then you have this broadcast gossiping, and then there is not so much improvement. And then the convergence rate is also quite bad, I would say. No? And the problem is that you have too many access to the channel, right? So you have a lot of coordination because it's like, these protocols, they assume that at any time point, there is more or less only one transmitter active, right? So if you go back here, you can see that, only one transmitter is active at any time point, right? And then this means that you need relatively many accesses to the channel. And this is what we know. And then in order to, say, improve or accelerate, this or enhance, this speed, the convergence speed, we have to minimize channel access to accelerate. We have to minimize the number of channel access. So this is basically also strongly related to some results in information theory. We know that the main bottleneck, because I was talking about this capacity notion, the main bottleneck, the main contribution to all the problems we have is interference, and we have to cope with this properly. So that's why we came up with another approach, which is first of all cluster-based gossiping. And here the idea is the following, that you have, first of all, you can see that in this phase, we call this uplink. So from devices to this cluster head, you have multiple connections active at the same time, right? And then you have, first of all, from devices to this one access point, which we called, cluster head, and then it computes something, and then sends back over this broadcast channel to all the devices. Okay, so but it's important for me that you remember that you have, in the first phase in each cluster there is two phases. The first phase is this uplink or multiple access channel phase when multiple links are active at the same time. So it means, like you have many people and they are shouting at the same time. Yeah? So first of all, it's a problem, right? Because, if you have a receiver, or another guy who should listen to all these people that who talk at the same time, the guy, it might be that he cannot or she cannot understand anything because she cannot separate, these signals. Okay, but let's, we take this and then see what happens. This was just, our convergence speed of this randomized gossiping and broadcast gossiping. And now if you have this clustering, then the point is the following, that you can dramatically increase, this convergence speed and convergence rate. And then, of course, it depends on the number of clusters, which is quite intuitive. So if you have one cluster, then basically what you can do, they all transmit to one access point and then to this cluster head, and then it computes the average and broadcasts back. So that's that. But you cannot have one cluster because in real world you have path loss limits. So if you have, if the area is too big, and if you transmit a signal, that you have path loss, so the signal strength decreases with the distance, right? So that's why you have to cluster, so to minimize the distance to the receiver. So that's why there are some limitations, and then you can end up with 3 or 4 clusters and so on. But the basic, the main message I would try to convey here is that we can accelerate the process dramatically by allowing multiple devices transmitting, accessing the channel at the same time. So it's like, multiple humans talking at the same time. But then, of course, the question is, how to cope with this interference, because they, basically interfere each other. So the key question is, how can in-cluster uplink communication? Uplink means, from here in this picture, from robot to a base station. This is from our lab, one of the labs picture, how this communication can be realized efficiently. And then recall that consensus only requires function computation. So in order to achieve consensus, I don't need to know the local states or measurements. I only need to know function of these states or measurements. So the idea is transmit only information needed for function computation, task-relevant information, and a paradigm shift is exploit interference superposition for computation. So here, why does consensus need less information? So imagine that you have n robots, and then they have, this n IID random variables, and they are Bernoulli distributed with probability 1/2. So now, if the task is, to transmit this to another place and fully reconstruct all the data, then if you compute the entropy of this, then you will end up with n bits. So basically, you have to transmit n bits to fully reconstruct, this random variables. So, but now, of course, if you only need the sum of these states, then the information required is this, the entropy of the sum, which is much, much smaller than n, especially if n is relatively large. Yeah? So it means transmit only the function, not all data. Okay, how to do it? So usually this is, the scenario here with the robot. So you have, this point here, this is the receiver, and then here you will say you have robots, and then they want to transmit some information. And then, okay, usually we say orthogonal transmission, avoid interference, like now is blue the arrow, so it means it's activated, and then you activate once after another, and then too much information sent, and then you compute the function. So basically you destroy information. Because, there is something called data processing inequality. If you apply, deterministic function, you cannot increase, the amount of information. But in this case, of course, if you compute the average, you will dramatically decrease, the amount of information, so you destroy information. So separating communication and computation is costly. We shouldn't do it. And this was also realized by NASA and Gaspar 2007. And key idea is compute during transmission. So basically, we try to use the channel, the air, for computation as a computer to compute functions. And I will explain how it works. So because here maybe this slide is might be too full, but I think the essence is here. This is the channel. So you see that the channel has something, it's a simplified channel, but it's enough here to discuss what the problem is. That the channel is some kind of if you transmit multiple signals, what the receiver observes is a weighted sum of the transmitted signals plus noise. So it's some kind of noisy version of the sum of the individual states. So that's why you see that, for example, if you are interested in average consensus, this structure of the channel fits very well to your task, which is computation of sums, and that's why you can expect this performance gains. However, there are some problems, but I'm not going to talk about this here. First of all, if you transmit signals, you don't receive, in general, if you don't do anything, you don't receive the sum of the signals, you receive weighted sum of the signals. And weights are realizations of a stochastic process. So they are random variables. So you have some kind of multiplicative noise in the channel. And then you have additive noise at the receiver. So you have to cope with this. You have to, more or less combat the impact of these noise sources. And then, of course, there is some synchronization, but we suggested, solution which is called over-the-air computation protocols. And here there are some papers if you're interested in this. And there's something called superposition theorem of Kolmogorov-Arnold, which states that every function, and here is a multivariate function, can be written, decomposed, like this. So you can see that here you have a sum of univariate functions. So here the function depends on, okay, in this case it's k arguments, not n. But here each function depends only on one argument. I will also, some people say that, I mean, it also this theorem says that, for example, you can have a deep neural network with one layer, and then and this outer function, and then you can reconstruct or approximate any continuous function, basically. It's not quite correctly, but okay. I mean, it doesn't matter here. Okay, so what I'm trying to say here is that for example, you can now, in the same situation like here, where you don't have any, you transmit the raw data at the same time. Here you can have some kind of pre-processing function at a device and transmit the pre-processed data, and then you have at the receiver some kind of post-processing function f, and then theoretically you can compute any nonlinear function, provided that you choose these functions appropriately. And there are many results in mathematics, but also we considered this, in the context of wireless communication, because this is a little bit more complicated, because in communication you have noise, so you have to cope with noise. So now if you apply highly nonlinear function to some kind of noise, then of course, I mean, the effect can be dramatic. So that's why you have to maybe focus on some class of functions and things like this. So anyway, it's what I'm maybe this concludes the first part, and I think the main takeaway is that if you have this coordination task, you have this collaborative robotics where robots cooperate for a common goal, then the communication is fundamentally different from communication where the robots generate independent data and then they compete for scarce resources, right? And then this fact can be used to reduce the amount of data transmitted over the wireless channel. And then if you involve, the superposition property of the wireless channel, or you exploit the interference for function computing, then you can expect dramatic performance gains. But of course, I mean, there are some practical issues, but this is that, of course, I mean, in practice, it's like, we have to cope with the synchronization, fading, and so on. So that's why, but still, we can observe significant performance gains if we, apply, those tools, and then just put some kind of consensus protocols on top of the wireless network. So here it's about strong integration of consensus protocols into the communication protocols. So, okay, I mean, here there are some other papers. I mean, one is also about max consensus. It's not average consensus, it's a nonlinear function. And then here we apply this to formation control with collision avoidance. So here you can see that you have, say, agents, and then they follow some trajectories to avoid collisions. And then in the end, they need to form this geometrical shape, which is hexagon in this case. So we implemented this at our institute here. So you have here 4 robots, this Segway-like robots, and then the goal was to form this shape here and avoid collisions also with these obstacles. And so this looks more or less like this. Here, I mean, you don't see this access point. And then they communicate. They don't communicate directly. They communicate via access point. So in this communication to the access point from device to this access point is just the uplink, and this is where we try to use this, exploit this interference to reduce the amount of data transmitted in this uplink, because this uplink will be a bottleneck in future. So here there is a target tracking using over-the-air computation. So you have, here this leader, you can see, and then they follow him. This is just, again, it's a consensus problem. And by the way, here we of course use camera-based system for positioning. So it's not, only a communication. Here we have to, know the position of robots. This position, they don't need to be communicated, but they have to be known. And for this, we used now, camera-based system. But in future, we would like to use radio or radar systems. I will say something about this later. So, and this long-term goal is like this. We have, these robots, and I said, okay, there's a base station, and here you can see there is one robot and robot 2, and then we have the cloud, edge cloud, and then there is a communication between the robots and the cloud, especially in the uplink via this access point. And then, of course, here, this is just, task-oriented communication or semantic communication. This is strongly related to what I was talking about. Basically, all this mechanism, how to coordinate and so on, are performed in the cloud, but some functions are performed here directly at the robot. And then, of course, there must be some kind of digital representation of the robot in the cloud. And of course, here you can also use the principle of semantic communication to reduce the amount of data transmitted to the cloud. So there's, the concept of distributed inference between device and edge. They shared model, common context in the cloud and the device. So in terms of, using the concept of digital twins, and less uplink via task-oriented communication. So, and then in future, we would like to have everything at one place. Now, perception, control, and task-oriented semantic communication. Control, of course, for example, in this example with this inverted pendulum robots, you have some kind of local controller to keep, this robot stable. But on top of this, you have consensus control to achieve this, consensus goals. And then for this, we use, this task-oriented semantic communication. This is what I was talking about. I wasn't, I didn't talk about perception. So you can, of course, use cameras, but in some cases, we have collaboration with the Charité, which is hospital here in, I think, even the biggest hospital in Germany. In general, they don't want to have cameras. And then also, there are many places where you cannot use cameras. So the idea is, for example, to use radar sensors and integrate these radar sensors with the communication. So in the end, you have one infrastructure for communication and perception. Yeah. So it's not new. This is about 6G. So 6G, as I said at the beginning, it won't only provide communication platform, but also computation and sensing. And then 6G will integrate radio sensing, transforming mobile networks into ubiquitous sensors to deliver new services, which is called network as a sensor. So here, in this, I think, AI-generated picture from my colleague, it's like, you can, for example, detect drones or even classify drones if you have enough bandwidth and track the drones. And then you can, in fact, generate the so-called Doppler delay maps. And then this is the basis for tracking, for classification, and other tasks you are interested in. So here you can see what we did, I mean, there is a guy running here in this lab, and then there is RU is basically access point, and the UE, this is a device. And then we communicate. This is just, some kind of this represents data, noisy data received at the transmitter, but still, I mean, it means that we communicate at one time, but we use also the electromagnetic waves to do sensing. So what can you do? I mean, you can reconstruct here. You have only one access point. You can reconstruct this delay Doppler maps. And here you can see some kind of, there are many reflections in this room. So you can see here distance. You have seen the reflections, but there is something here. And if you look at this, this is due to the movement of the guy. So you have Doppler shifts. Yeah. So you get the Doppler shifts, and then you can use this for ranging or some other things. So our goal is really to have, in the end, this base station, or maybe 2-3 base stations, they collaborate, they just, receive and transmit the data, but also they provide perception. I mean, our dream would be to get rid of the cameras, to have one infrastructure that is doing everything. But I don't know whether this is feasible. This is just still research, because we need here in many use cases we need very precise localization. But sensing is more than localization, right? It's detection, it's classification, and things like this. And for this, of course, I mean, we also showed that this can be used, and then we can, for example, reliably detect whether a patient is a bed in a hospital or not. I mean, this is, you don't need a camera to do this. Okay, but if you are interested in high precision, then you need more bandwidth. And then more bandwidth is if you go to high frequencies. Here, high frequency is 160 gigahertz, the bandwidth 4 gigahertz. I mean, now we are going to 8 gigahertz. And here, what we can achieve at the moment is a range resolution, around 3.75 centimeters, and velocity resolution, like this. So we can improve this because this is just only sample based. There is no algorithm on top of this to improve this. So we can go easily below 1 centimeter, but the question is whether this is, enough or not. No? And here, okay, I mean, there's this simple demo. So you can see here Michael from group leader in my department, and he is walking. We can just range him. And then on the left-hand side, you can see delay Doppler maps. And this is, the basis for classification or other tasks, like ranging and so on. So, okay, I mentioned that we are interested in collaborative robotics, and this sub-terahertz sensing can be, for example, used in the medical context to capture vital parameters here. Okay, 160 gigahertz, this should be too low. I mean, maybe you have to go even to higher frequencies. So here we have these robots from, I think, KUKA, and then they can be equipped with this sub-terahertz technology to do this, non-invasive sensing, multi-perception, and so on. So this is for example, this is one example how we would like to apply this technology. But also you can, for example, have a communication infrastructure, and then you can do monitoring in the night. Okay, so for this, I mean, maybe cameras, it's not the best solution. And then you can, for example, analyze liquids and things like this. This is what we can do with this technology. Of course, this is not related to robotics, but just wanted to mention. Maybe somebody is also interested in this topic. Okay, so as I said, I mean, I was talking about this mainly about this consensus-related application, but also what we consider is say control of, for example, robots via wireless channel. And here we demonstrate a normorphic edge inference testbed for semantic aware wireless communication implemented in a real robotic system. And here you have event-based sensors generate sparse task-relevant features. And for this, we use, the spiking neural networks because they consume a small amount of energy. They are highly energy efficient. And then this signals, output of this spiking neural network are encoded and transmitted efficiently over the wireless channel for distributed inference. Here, the highlight is, and I think that this is where I think that we need some kind of collaboration between robotics and communication because we have this functional split. I mentioned this at the beginning. So there is not that we transmit, here you have a robot, this is a device, and then we don't transmit raw data to the infrastructure for inference network. We have some kind of semantic encoder. We have some kind of encoder on the device side. So basically it's pre-processing. It's a compression of the data, which then to extract semantic and transmit over the wireless channel. So from our perspective, the goal is, of course, to reduce the amount of data transmitted over the channel. And then here the task was gesture recognition. So I don't have here a video, but basically you control this robot by gestures, and the task is not to track the hand, but just to classify between gestures. And then, of course, I mean, this is, task, if you apply task-oriented communication, and they say that, the task is classification and not, tracking of the hand or something like this, then, of course, you can dramatically decrease, this amount of data transmitted, and this is what we exploited in this demo. So another demo shows split inference for integrated sensing and communication in network robotics scenarios. Radar sensing and neuromorphic processing extract task-relevant features at the device, which are then transmitted to the edge for joint inference. So basically, I was talking about this sensing, and then here you can also apply these principles of, say, task-oriented communication to task-oriented sensing. So you don't reconstruct the whole, say, room where the robot is. You only extract features that are relevant for the underlying task. And then, of course, I mean, here there is also this issue about related to the functional split, what to do on the device side, what to do on the infrastructure side when the channel between device and infrastructure is just wireless channel, which is noisy and not nice for communication. So, you can lose packets, you can lose links and things like this. You have to cope with this. Good. And then, okay, so what we have, what we come up is this, this slide illustrates the overall architecture for edge learning and inference in large scale robotics. We have some kind of simplified version tailored to the application in robotics, but this is more general. So you can see on the left-hand side, we have inference, orchestration, and also model training. Models are trained either centrally or at the edge and so on. So here in the middle, you have some kind of model management. The handles deployment, compression, and continuous data collection. This is essential to adapt models over time and to distribute them efficiently across the system. And here on the right-hand side, we see the radio access network. Here, communication is no longer purely bit-based. Instead, we introduce a semantic layer where only task-relevant information is encoded and transmitted. This is complemented by AI native physical layer processing, which enables efficient use of the wireless channel. I mean, this is what I was basically talking about, and the key aspect is the convergence of communication and computation, which you can see here. So I think this is basically the last slide. We, of course, also planning, the labs, new labs here. You can see visualization here that we will have a lab here in collaboration with the Charité for medical applications. And here also lab, more general for also, I have to say, manipulate robots and things like that with Marc Toussaint. But we are interested in also other, say, scenarios or applications in the context of this collaborative robotics. But as I said, we look at this, we are not guys who build robots, we just interested how to provide a robust and efficient connectivity in the face of, for example, errors in the transmission or scarce resources like spectrum, energy, and things like this. So if you are interested, there is also, this was, the work was mostly supported by the BMFTA. This is the Federal Ministry for Research. I forgot. But the BMFTA, I hope you know. And then we have something called XGRIC, is Research Innovation Cluster. Now it's a technology cluster where we try also to say, to transfer, these key technologies to practice and so on. So thank you for your attention. And maybe there are some questions.